Hi guys, I'm back. All right. So this one is about nerve. So let's see, share screen. This one here, share. All right. So nervous system. We will talk about the brain, spinal cord, our nervous system. Okay. So in the in the brain or in the central nervous system, our nervous system can be classified as central and peripheral. Just a central nervous system, in the brain, the spinal cord, we have two type of nerves, or two type of cells, So one is the neurons, and the other is, and then another group is called glial cells. So say in our brain, we thought that it's all neurons. It's not all neurons. It has neuronal cells as well as glial cells. So we will first talk about some neuronal cells. Neuronal cells are those can be excited and like muscle, excitable. And the glial cell are the supportive cells. Glial cell has three types: astrocyte, myelin cells, and the microglia. So these are supporting cells in our nervous system. They do not transmit electric signal. They are not excitable. Their function is to support our nervous system. So it's also important. So we will talk about this. So let's start by talking about the neurons or neuronal cells. It's the same thing. So neuron, this is one typical neurons, and all cells has a cell like a body has a nucleus. In the neuronal cells, in a neuronal cell, the cell body is also called soma. Okay, sorry. And here is the nucleus. It has the extended part of the cell called axon, as well as a lot of these branches is called dendrites. So that's a typical neuronal cell. Soma, axon, dendrites. Neuronal cells function is to transmit electric signal. So we talk about how our brain can control our hand to grab a water bottle. So that transduction is not like magic. It has to transmit through a line. So it's very much like a landline. It's not like cell phone, like no line. This one has to land as a line. So from the brain, send through this this circuit, this fiber circuit, electric signal will transduct through that core electric line to the lower motor neuron in the spinal cord, and then send out signal to the axon, through the axon to the muscle. So that's typical neuronal cells. This portion dendrites are the one to receive signal, and when it receives signal, it will collect it and then send out a signal. So if there's any action potential, if it's got excited, this excited signal will be generated in the initial segment or axon hillock. This initial segment of the axon here is where we generate the action potential. The action potential will then travel down to the axonal terminal. Here it will release neurotransmitter. And if this one happens to be muscle, then the neurotransmitter will act on the muscle. So typical neurotransmitter like acetylcholine, that's the one to act on the muscle. But there are so many different types of neurotransmitter. So here is that when signal transduced to the axon terminal, it will cause the release of neurotransmitter. And if the neurotransmitter, if this axon terminal targets the muscle, then the neurotransmitter will act on the muscle. Or this axon terminal may communicate with another neuron. So this is another neuron. And here is their dendrites. Like this one here is dendrites. So neurotransmitter may act on another neuron. So this is another neuron. So it could be the muscle, it could be the neurons. This region is called synapses. Synapse. This region is called synapse. This gap is called synapse. This one synapse. So let's look at this synapse. So this synapse is where we see the presynaptic terminal. This one is the axon terminal. Presynaptic, basically, this one is the axon terminal. That's where we see this right here. That's where we see it here. Okay, so signal coming down here. And here we then release neurotransmitter. So this presynaptic, postsynaptic, presynaptic portion is also part of the axon. It's the axon terminal. And the postsynaptic are dendrites. So this portion is the dendrite. D-E-N-D-R-I, dendrite. D-N-D-R-I-T-E, sorry, T-E, dendrites. So that's right here, dendrites. So axon, dendrites. So pre is the axon, post is the dendrites. So here, presynaptic is the axon, postsynaptic, this is dendrites. Dendrites, okay. This is actually, here, let's look at this one. This is presynaptic axon, presynaptic, this is post. This post portion is not just dendrite. It's dendrites. Majority is dendrite, but it can also be soma. Soma can also receive the neurotransmitter. So dendrites, soma, but not axon. Axon has no receptor to receive neurotransmitter. So you see that here on the dendrites and the soma, here we see this one is called a spine, dendritic spine. So this one is spine. So here, dendrites has this extrusion portion, like pop out. So it's like very much like our ear, like pop out to here, to receive neurotransmitter. So here we see the spines locates in both dendrites and the soma. So here we have the dendritic spines as well as somatic spines. And so whenever you see these spines, you know that it contains neurotransmitter receptor, because that is the postsynaptic site where we will see the neurotransmitter receptor to receive these neurotransmitters. So this is the synapse. This is the synapse right here. So if we expand this view here, we can see it here. So basically that when there's an action potential travel down to the axon terminal, and it will cause the neurotransmitter to be released. Right here, neurotransmitter to be released. And to release that, we need to undock these vesicles, just like we have talked about in the motor system. So it will, to undock these vesicles, we need to open up the calcium channels so action potential travel down here. Here we have a voltage gated calcium channel. It will open to allow calcium coming in. Calcium coming in, then it will free these vesicles. Then vesicle will be freed, neurotransmitter will be released. Neurotransmitter will go to this is the synaptic cleft or synaptic space. So this is gap. Action potential would not jump over. Action potential only remain in one cell, but not to the other, because these two are not connected. Now, this one will then release neurotransmitter. Neurotransmitter they will then act on the postsynaptic site. So this one is a spine, spine, and here we see this neurotransmitter receiver, neurotransmitter receiver, right here. And in muscle, in the skeletal muscle, what's the neurotransmitter? Acetylcholine. That's right. Good job. What's the receptor? Nicotinic acetylcholine receptor. That is right. Good job. Yeah. So that's a good all time that you only need to memorize two and the related terms. In the nervous system, we have a lot more. We have this neurotransmitter can be dopamine, can be serotonin, can be norepinephrine, glutamate, and the receptor have a lot more different variety. So that's why our nervous system is so complicated. People think that they can generate artificial intelligence, right? Like AI system to stimulate our brain. It's very difficult. I mean, our brain is very dynamic and also very complicated. It's not just physics, it's chemistry. We have so many different types of neurotransmitter, and they can be reused, be truncated, be modified, and the receptor also can be reused, can have phosphorylation on it, can be enhanced. So our nervous system is very complicated. But that's how we operate. This is how we operate. Our nervous system, basically, that's how we operate. We have a generate action potential and go through these synapses, and through this release neurotransmitter. These spines, these circuits are dynamic and not dynamic. For example, let me ask you a question. Like, do you remember your meal, your last meal, like lunch or breakfast or dinner if it's late? Do you remember? You remember, right? Then how do you remember it? How do you remember your meal? The way you remember it is that you wire a circuit in the brain. And so this time you wire it to like a burger. And because you already have a memory of burger, but you need to link it, say breakfast burger, link it. And so you memorize it, you build a circuit. But if you give it time, this circuit can become not so important. Then you forgot about it. But if you just link it, you memorize it, and then you forget about it. And you memorize it like number, like somebody told you that this is my phone number. You memorize it, you have a memory about these digits of number. Then you link them together, you memorize it, you generate that circuit. But give it time because you don't use it, you forget about it. But if you use it many, many times, that connection becomes stronger, 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 very tight. Then you will be very difficult to forget about it. So in the human brain, memory is formed by a circuit connection, a wiring. So it's very, very different from our cell phone. Like if you want to take a memory, if you want to take a picture, save it as a memory. We do it as a software. Like we take picture and it will be saved in the memory. In the brain, it's not like that. It's rewiring. When we memorize one thing, we generate a circuit through this connection. So this connection is very dynamic. If we do this one in our cell phone, it will be very much like if we want to memorize a picture, we will have to open it up and then rewire a circuit and then put it back. Then it have a new memory. But in the brain, we do this all the time. We have these new circuits connected, disconnected, connected, disconnected all the time. So that's how we run. That's how it works in the brain. All right, so let's talk about this neurotransmitter. So basically, that's very much the same thing here. Action potential travels down to the axon terminal, opens up a calcium channel, then neurotransmitter got released. Vesicles go through this exocytosis, release the material. Here, neurotransmitter then be released. Released from the presynaptic to the synaptic space, synaptic cleft. So only one thing you need to memorize is that these are all in the presynaptic. And the presynaptic is part of the axon. And calcium channel is needed, otherwise these vesicles would not be moved. This is very kind of universal, like we see this one in motor. Any time when you need to release vesicles, basically calcium needs to come in. Don't get confused by the calcium we mentioned in the muscle where it's released from it's used for the troponin. So that calcium is from the troponin is used to open the door to X on the troponin, move the tropomyosin to allow actin to be seen by myosin. So that calcium coming from the sarcoplasmic reticulum. So it's different. It's a different group of calcium. This calcium is to undock the vesicles right here, to undock the vesicle. Now, when we have this neurotransmitter, it will act on the receptor, right? And then that's in the postsynaptic site. Now, let's look at this receptor. Receptor has two types. One is called an ionotropic receptor. It means that ion will go through. So this ion this is basically an ion channel. So this is an ligand-gated ion channel. That ligand is this neurotransmitter, binds on it, open the channel to allow ions to go in. If this ion happen to be sodium, positive charge ion, then it will increase the memory potential because it's positive, increase the memory potential. And if it's above the threshold, it will trigger an action potential. So that's a type of the receptor, the ionotropic receptor. Another type of the receptor is like this one here. It doesn't come with an ion channel. So when this neurotransmitter binds on it, got received by this neurotransmitter receptor, it's not going to open a channel right away, but it's very much like a knock the door, or there's a button right here, you pushing like that, and then it will cause something happen in the postsynaptic side. So this receptor binds on it, and then it will cause events, cause some second messenger. There are a lot of chemicals in the inside of the cell to serve as the second messenger. So this type of the receptor, which doesn't come with a channel, ion channel, is called a metabolic receptor, metabotropic receptor. Right here, metabotropic receptor, ionotropic receptor, and the metabotropic receptor. So there are two types of receptor. And the response is increased memory potential, biochemical cascade like second messenger, gene expression. So that may cause your neuron to, provide some gene expression. Gene expression means that it will synthesize proteins. Protein synthesis is from DNA to RNA to protein. And so that process is a gene expression. So that's how we build the enhanced circuit when we have this transduction. In the beginning, it's very weak conduction because we don't do this very often. Like the first time you cook, you don't do this very often, and so you make mistake because this wire is very weak. But if you are like a chef, you like cut the veggie or something, and give it time, you become very good at that. You cut like a cucumber or something very quick because you already built that circuit very strong. And the way we build circuit very strong is that our postsynaptic site can have a gene expression to produce more of these transmembrane protein. These receptors are all proteins. So we can, when there is a connection, it can trigger a gene expression to put more of the receptor here. So by having more receptor in the postsynaptic site, we can enhance this circuit. And so you will become very good. If you play basketball, more practice, you have more receptor, you have stronger connection, and you got better. And you got excited. Sometimes this one can be part of the reward circuit. So you feel joyful and you do it more because you enjoy it. You're excited. Your reward circuits are also, part of it. And then you do it more, and that a positive feedback, and that will cause more of this receptor, and the circuit becomes stronger, and you're becoming better in this repetitive process. So two types of receptor: ionotropic receptor and the metabotropic receptor. Ionotropic receptor come with an ion channel. And so this one is also called a ligand-gated ion channel. And depending on the ion, if it's positive, it can increase the memory potential and trigger an action potential. So that's also a part of the excitatory stimulus. It could be the negative ion, such as Cl- chloride. If it's chloride, then chloride coming in will make the memory potential to become negative, to become hyperpolarized. And so it will make it not away from the threshold. And so that will make it less possible to become excited, and that will be an inhibitory stimulus. Metabotropic receptor will induce a second messenger. These proteins are typically used G protein. So this receptor is also commonly called, so this metabotropic receptor is also called a G protein coupled receptor, GPCR. So just, easy question is like, which one is related to G protein coupled receptor, GPCR? Is it ionotropic? Is ligand-gated ion channel? Is this metabotropic? The answer is metabotropic. So that's two types. Here are just some pictures showing you, you have some visual idea what's this like. We saw this last time. This is a nicotinic acetylcholine receptor. Acetylcholine binds on it, opens the ion channel. See that the receptor come with the channel, ion channel. So this is an ionotropic receptor. Another type is the metabotropic receptor, like this one here. Acetylcholine binds on it, so it's same acetylcholine, but different receptor. And then it doesn't have any channel, it will activate G protein. So that's why this one is also called a G protein coupled receptor, G protein coupled receptor, GPCR. And then this G protein will be split, and one of it will flow to the neighboring ion channel. So it could be a potassium channel. So if the potassium channel open, will potassium going in or going out? In the cell, we have a lot of potassium. So when this channel open, potassium will flow out because of the high concentration. And the potassium is a positive charged ion. So when potassium flow out, it will make the memory potential to be less positive, to be more negative. So it will cause it hyperpolarization. So this will be an inhibitory effect. So same neurotransmitter acetylcholine can have an excitatory effect like this one here, more positive charged ion going in, or it could be an inhibitory effect, make this potassium ion to flow out. It all depends on the receptor. It's not just the neurotransmitter. In the muscle, we don't have this type of receptor, but in the nervous system, we do, we have different type of receptor in the nervous system. So this is just a side-by-side comparison of this ionotropic receptor. It's also called ligand-gated ion channel. This one is a metabotropic receptor. It's also called a G protein coupled receptor. So as we see before, this receptor can induce an depolarization, like make the memory potential to become positive, above threshold, trigger and action potential. So that trigger and action potential is a depolarization because memory potential is negative. So there is a polarized. We depolarize it to make it not so negative. Depolarization or hyperpolarization to become more negative. So it could be an excitatory or inhibitory effects. So in one cell, neuronal cells, on the dendrites, on the soma, where we see these spines, where we see these receptors, we may have excitatory, like green light here, or inhibitory, like a red light here. So one neuronal cell can receive so many input, so many input, and these circuits are dynamic all the time. Dynamic all the time. Sorry, it's dynamic all the time. So one thing about the memory is that you read something, you understand something like G protein coupled receptor, GPCR. And so you start to build that circuit. GPCR, these 4 letters was already memorized in your brain. You just connect them together, GPCR. And then you hope that you will wish that during the quiz or during the exam, you can retrieve that memory, okay? And how can you improve that memory? How can you improve that memory? This one has been studied for a long time. Like, how do you improve your memory? Why do I talk about that? Because it's practical, right? If you know how to improve memory, that's not just for this class. This will be very beneficial for your whole life. So improve memory has 2 ways. This is science. This is science-based, science-backed approach. The first one is repetition. So it's just like a cook, like playing like instruments. You repeat it, then you enhance that strength. That's one way. The other one is called theta wave. So our brain has an alpha wave, gamma wave, theta wave. So that wave, if that wave is harmonized in a way that can improve your memory, how can we achieve that? Sleeping is an important instrument. Sleeping is the best way. When you sleep, you will have the brain wave to become theta wave, and that can consolidate your memory. So that's why I'm saying that if you are in my classroom, my policy is you are allowed to sleep, okay? But you're not in my classroom right now, so you can sleep at home. So sleep is important. You can, before you go to sleep, read something difficult, and then you go to sleep. That memory, that weak connection can be consolidated very well through sleeping. So I know part of you have tough life, like work. Sometimes we don't have choice, but if we have a choice, when we have a choice, the first thing you will do is to have a good sleep. Yeah, it's better than anything else, better than diet, better than exercise, better than watching TV. Have a good sleep. All right, so one neuron receives a lot of inputs. Okay, a lot of inputs, like hundreds, thousands inputs. These inputs, part of it could be excitatory, part of it could be inhibitory, okay? And then these neurons will take these inputs. Some of them will increase memory potential, depolarization. Some of them will cause it decrease memory potential to be hyperpolarized. And overall, they will sum it up, right? Some increase, some decrease. And if the majority is increased and increase above threshold, it will trigger an action potential. Action potential will be triggered in the initial segment of the axon right here, initial segment of the axon. And then that will travel to the axon terminal. So the receptor can have a excitatory event or inhibitory event. This excitatory potential is also called excitatory post-synaptic potential, EPSP. For example, if we open the ion channel for sodium, calcium, these two are very typical one, then we have the depolarization because it increased, it's positive and it flows in, so it increased memory potential, so it's excitatory. If on the other hand, if it's increased the ion channel of chloride or potassium, chloride is negative, it flows in because in the cell, everything else is less. Only potassium is more in the cell. So when you open the channel, they basically all flow in. Sodium flow in, calcium flow in, chloride also flow in. So that will make it more negative. Or if we open the channel, potassium channel, potassium is more in the cell, so potassium will flow out. And that will also make the cell become more negative. And that will cause it hyperpolarized, and that is an inhibitory post-synaptic potential, IPSP. So some of it could be the excitatory, some of it could be inhibitory. I want to bring you another two important neurotransmitter that is called glutamate. Because in the central nervous system, glutamate is the major neurotransmitter to induce an excitatory event, to induce an EPSP. So all this green could be provided by the neurotransmitter glutamate. So this term, you need to memorize it. Must. When you take neurophysiology, one thing you need to memorize is to understand these new terms. If you never heard about it before, glutamate is the excitatory neurotransmitter. And inhibitory neurotransmitter, the major one is called GABA, G-A-B-A. This is the major inhibitory neurotransmitter in the brain. So this will be in the quiz question, okay, or in the exam, that which neurotransmitter, because now we learned 3 neurotransmitter, acetylcholine, glutamate, GABA. And the question would be, which one is used for neuromuscular junction? Ta-da! Which one is the major excitatory neurotransmitter? Ta-da! Which one is the major inhibitory neurotransmitter? Ta-da! Okay, you need to know that. When the cell receives all these inputs, the summation of it would define that whether this cell will generate action potential or not. And that summation will occur here in the initial segments of the axon. Because all they can receive signal, the location where they can receive signal are either in the dendrite or in the soma. Only dendrite and the soma contain spines. That is also a quiz question. Like which region we don't see spines? Soma, dendrites, or axon? Axon, we don't see spines. Axon only transmit, they don't receive. They are the one to send out signal. So around here, we receive the signal. And if that vote, here is a vote, everybody vote. And if it's higher than the threshold, it's a yes. Then here is a region that will trigger an action potential and then propagate along the axon toward the axon terminal. And in the axon terminal, what they do? Release. They will open up calcium channel, then vesicles are freed to the axon terminal, release the neurotransmitter. So this one is important. Where do we generate in the neuron? Which region generate the action potential? It's an initial segment of axon, or axon initial segment, same thing. This will propagate. This one is called impulse. So the idea is that action potential travel from the initial segment of axon to the axon terminal. This is one-way propagation, because in the axon terminal, they don't receive signal. It's only deliver, it's not receiving. So signal always coming from the soma toward the axon terminal, but not the other way around. So that's the neuronal cell. And let's talk about the other group of cells. They are called glial cells. They are, you have one slide, but that slide I removed. You will see it later because that was some like accident that I put that slide here. So, but don't worry, we will talk about it later. Now let's look at these glial cells here. So glial cells are another group of cells in the brain, and the name coming from the glue. So they are supportive cells in the nervous system. They are not excitable. They don't have dendrites, axon. They are just over there to support our nervous system. There are 3 types of the glial cell. Myelin cell, this one wrapped around the axon. We have 2 types of myelin cells. Oligodendrocytes, this one is a myelin cell in the central nervous system, meaning that it's in the brain and the spinal cord. Schwann cells are the myelin cells of the peripheral nervous system. So remember that we have the motor neuron, right, in the spinal cord. Let's see, where is that? So this one is a spinal cord. okay? Motor neuron. Motor neuron send axon to the muscle. So this one is out of the spinal cord. And here, the myelin, or the myelin around here is the strong cell. And also we have the astrocytes and the glial cell. Astrocytes is the star. Astro is like star-shaped cell body, and a large number of processes. So it's if we look at it compared to the neuron also look like star, right? So how can we distinguish these two? These two, the difference is that neuron has very, if we look at the histology, I mean the microscope, we can see neurons have a lot of spines on it, but astrocytes don't. Astrocyte has very smooth surface. Don't worry about the microscopy on this one because we are not going to do any like a lab on them to distinguish which one is which one. Okay, but just keep in mind that that's how they are distinguished. So astrocytes also a star shape. Okay, their function, myelin cells is to wrap around axon. Astrocytes is this like the manager in the nervous system. They provide nutrients. They regulate a lot of nutrients in the environment. Then the microglia. Microglia is part of the immune cell. So this is not really like related to the nerve. This one is because that, remember that we talked about that blood has some white blood cells. One of it is called monocyte. Monocytes can move away from the blood vessel into the local tissue and reside there. So they can move. They can stay in the blood, or they can go to the tissue. So these microglia are that monocytes. Then, because the brain has very tight, like a border, they prevent virus, bacteria going to the brain. So the vessels are very tightly controlled. But when the brain development in the early stage, like in the infant, that tight control is not completely finished yet. And during that time, our monocytes can leak into the brain and stay there. So that is the immune cells from the blood. That's part of the blood cells. And they remain there. They are called microglia cells, microglia. And they are there to conduct the function for the immune purpose, like to clear away the debris. Usually the brain, we don't have a lot of like infiltrated particles. It's not like our intestine, like our skin that has a very higher chance to see a lot of, or to see like bacterial virus to infiltrate. In the brain, it's all very well protected. So that microglia is part of the immune cells. So myelin, we have the central nervous system, CNS. The myelin in the CNS, central nervous system, is the oligodendrocytes. The myelin in the peripheral nervous system, PNS, is the strong cell. So this one is the axon, but no. This one is a neuron, and this is axon, and axon wrapped around the myelin. So here is myelin wrapped around it. This one is axon, this myelin. So these are two different cells, one wrapped around the axon. In the central nervous system, one oligodendrocytes can wrap around multiple axons. In the peripheral, one Schwann cell only wrapped around one axon. And when they wrap around the axon, they are not completely wrapped around it. So it's very much like our like wire, right? Inside of it is a copper, like a metal wire. Outside we have this plastic thing. So this plastic thing is a myelin. But in the wire, we have it all wrapped around. But in the nerve, we wrapped around it not completely. We have some opening here. So this is called a node of Ranvier. Yeah, node of Ranvier. Node of Ranvier. And so this is a node of Ranvier right here, node of Ranvier. And so node of Ranvier is, what's the purpose of it? It's for the action potential. So let's say, remove this one here. So basically that, why do we have it open? Because action potential, remember action potential? We have the depolarization and the repolarization. Depolarization, which channel open? Which channel open in the depolarization? Sodium, good job. Which channel open in the repolarization? Potassium, okay. So we need to have a channel open to allow extracellular space, interaction with the extracellular space. So that region we cannot wrap around, we need to leave it open. And so here in the beginning of the axon, we have this action potential generated right here. And here, all through this segment, it's all wrapped around. So it's really difficult for it to have any action potential to be induced. But that can be induced to generate an action potential here. So this has to be close enough, not too far, because if it's way too far, this induction cannot induce anything. So it has to be close enough. And if it's close enough, then here feel, because this is electric. Electric has like a electric wave. So it can kind of like induce. It's very much like a magnet, right? So you have something magnet positive here. You don't need to close to another magnet to get attraction or rejection. Through a distance, that magnetic like wave in a way can induce the other one. So that's same thing here. Here we have electric signal positive, like electric potential right here, and then that can induce the other one if it's close enough, right? So here it will cause that to this region will feel here that action potential, and here in this node Ranvier it's open, and during this node Ranvier in this region, it will have a lot of sodium channel and the potassium channel. So when they feel here action potential, they feel it, and then if that feeling is strong enough, then it will trigger an action potential here. And so sodium open, potassium. So it will also generate, let's put it here, it will generate another action potential here. And that do the same thing here, cause another generated action potential, generate another action potential. So this conduction is not a propagate like we saw before, like we saw it here. It's not propagate. Because the thing about the propagation is that this will decay, right? Action potential, give it time. It's like if you play a game, like you try to murmur to the next person and transduce that signal to the next one. By the end of that line, the person will have totally different story, right? because that transduction will decay, signal will decay, and some noise will come in, and so it will alter the signal. So this kind of transduction is not very efficient, and it's also cannot propagate very long. With this one though, this one will be very strong action potential, so it's either 1 or 0. So once it's full or none, all or none, right? So it will generate action potential. And so that will remain that strong signal throughout. And also it will be fast. It's not propagate, like go through every inch of the cell membrane. It will jump. So that will be much faster. So that's the node from Ranvier, and that's exposed to the extracellular space for about 1 micrometer. So that's some opening there. In this region, it has rich sodium channel, and so it can generate a depolarization. This region also have a lower threshold for action potential. So that induction doesn't have to be very strong. A little bit induction can be strong enough because the threshold is lower to generate action potential, So that's how when we touch things, our brain immediately know it, right? Because that transduction is through a myelinated axon, and that transduction is very fast. So that's called a saltatory conduction. Jump through the nodes of Ranvier. This is no myelin, so this is propagation. This one is slow and also prone to noise. It's easy to get noise signal into it. This one is stronger, signal is strong and also fast. So basically it's the same thing here. It will induce it, jump through it. So that's basic nerve system. That's basic neuronal cellular system. All right, so the next step is to expand it to our body, our nervous system. So in our nervous system, this one is the diagram of that nervous system. We have the nervous system, we have the central nervous system. Central nervous system include the brain, the spinal cord. Peripheral is the one to interact with the outside world. So that peripheral has two portions, two branches. One is to feel, one is to act. The sensory, the motor. So sensory is the one to receive signal from the outside world. You can smell, you can see, you can touch, you can feel. It's all sensory, and that sensory is part of our nervous system. So that sensory nerve has two branches. One is called dorsal root ganglia. This one is coming from the spinal cord, dorsal root. And the cranial nerve ganglia. Cranial nerve sensory from the eye, from the ear, from the nose, from the tongue. So these are the cranial. And also vestibular is vestibular, the one to detect our body balance. So that's the cranial. And the dorsal is one that's our somatic, like touch. This one has a lot, you can feel not just the texture, the pressure, you can also feel the temperature, can also feel the pain. So we have the different like receptor in our skin to detect different kind of stimulus. the motor also has two branches. One is a skeletal muscle, skeletal motor system. That's one is the voluntary nervous system that we reach out to a bottle of water, and because we know that's what we are doing. Another portion of this motor is the autonomic. So this skeletal motor is the one to control this skeletal muscle we just learned last chapter. Autonomic is one to control the other two type of muscle, cardiac muscle and the smooth muscle. So this autonomic control our heartbeat, control our GI system, control our gastrointestinal, and control our vessel. So this one is done, right? This one we learned this one already. This portion is, we learned this already, okay? We didn't relearn other yet, but we learned this one. This one, we will talk about this one here. So autonomic also has two branches. One is called sympathetic, the other one is called parasympathetic. We will talk about that. But before that, we will first talk about this one here, sensory. So we have the sensory and the motor, basically right here, sensory and the motor. These two basically complete our, motor has two branches, sensory has two branches, but sensory and motor basically is all what we do. Sensory, motor, and the center. Sensory, motor is peripheral and the center. So it's right here. Sensory, motor, and the center. Central nervous system. So we see, when we see things, we will think what it is, right? We will retrieve our memory to remember, we see this before? Is this my cup? Who took my cup? And then we grab it, right? This is my cup. Or am I hungry or am I thirsty? We would think. We will interpret our observation, and then we will make a movement. So basically that's all here, sensory, motor, and the central. So we already talked about the motor, right? So let's spend some time about the sensor here. Sensory, as I said before, sensory nervous system receives different inputs from the outside world. Could be the touch, could be the eye, could be the seeing, could be the taste. This is a chemoreceptor because different tastes coming from the chemical components in the food. And the nose, smell, this is also chemoreceptor. A lot of this receptor has strong adaptation, means that you have perfume, right? You put the perfume on, and for a while you feel like, I didn't smell anything, and then you put more, and moment later you feel like, I don't smell anything. Then you put more, but people surrounding you, when they first see you, they was, oh, so strong, something like that. Because your nose will get adapt to it. And so this one is especially true for the, yeah, so that's the, because there are a lot of like theory behind it, like shark can smell blood, but they don't get adapt to it. That's something that people still study, why shark can smell blood, but they don't get adapt to it. That smell is going get stronger and stronger. It's not going to be adapted. All right, so let's look at this sensory signal. Just pick one as example, like tactile receptor in the skin. This is a part of the somatosensory receptor in the skin. We have different receptor, and so these are all like a mechanoreceptor. This is not chemical receptor. They are mechanoreceptor. Means that their stimulus come from the physical bending or physical bending on that receptor. So when we touch things, there will be physical bend on the skin, and that will trigger an action potential to send out signal to the brain. So this one is one of the example of this one. There are so many receptors you don't need to memorize at all, like Messenger corpuscle, Ruffini ending, free nerve ending. Don't need to memorize all this, but the idea you need to know that basically they are banded. So like this one here, this is one of the receptor. When they are banded, then when they are banded, some membrane become more open, and when it opens, sodium coming in, and that will trigger a potential. This one is called receptor potential. So when the receptor receive a stimulus, it generates that potential. Is called receptor potential. If this receptor potential is above the threshold, it will trigger an action potential. Then here is action potential. Action potential will then propagate the signal back to the brain. There are so many different receptors. Different receptor has different adaptation. Adaptation is one that our receptor give it time, it will start to become numb, don't respond to the stimulus at all. So for example, that some receptor, so here is the impulse per second generated by the stimulus. For example, some like a hair receptor drop to 0 very quickly. Means that I put a hat on, my hair receptors feel it. And so when you first put it on, you know it. But give it just very quick, like 1 second, you don't feel it at all. They don't cause any stimulus. So so if you are looking for your head, look at your head, might be already on it. But other receptor can have a slower adaptation. It would reduce the response to it, but not totally 0. When we have this receptor, it will send signal into the brain. So here is the sensory pathway. 2 things you need to know is that they enter into the body through the dorsal horn of the spinal cord. Motor neuron is in the anterior horn. Sensor is in the dorsal. So they come in the dorsal. And the second thing you need to know is that the sensory signal is processed in the opposite side of the brain. So signal coming in and go to the opposite. So here is the brain. Brain has different lobe. Frontal lobe, here is the central sulcus, like there is a line in the center, and the parietal lobe, occipital lobe, temporal lobe. So in the brain, we have this cortex has different zone, different parts. And different parts, not just anatomical difference, they are also functional difference. Frontal lobe is for action. The back portion, parietal and occipital, is for feeling. So this one is action, this one is feeling. So action include the motor and also decision making. So frontal lobe is important. In the frontal part is for decision making for the judgment. And here earlier, this portion is the motor cortex. Here is the central cortex, sorry, sensory cortex. And then here, occipital is the visual cortex. So sensory cortex are here in the parietal lobe. So here is the parietal lobe. We have the somatic sensory cortex. So the quick question could be that which region is the region to process our sensory? It will be the opposite side of the brain, and it will be in the parietal lobe. So sensory and motor, when we feel it, we send signal to the opposite side of the brain, process in the parietal lobe. The motor also coming from the opposite side to control the other side of the muscle control. So this one is motor. Motor is, we mentioned before, this one is kind of repeat it. When we decide to do something, our brain will send a command to the spinal cord. Then in the spinal cord, the lower motor neuron are located in the anterior lobe of the spinal cord, and that will send out axon to the muscle. And a group of muscle work together is called a motor unit. So that's the nervous system. Okay, so here, kind of like overview a little bit. The sensory motor, right? We talk about the sensory, peripheral into the center in the opposite side of the brain, and go into the part of the spinal cord is the dorsal horn or dorsal root of the spinal cord, and the motor is coming from the anterior and or ventral in the front. And then that motor control the skeletal muscle. So these are all talked. Now let's talk about this autonomic nervous system. This autonomic nervous system is the motor. Autonomic nervous system is the motor control. It just not control the skeletal muscle, but control the smooth muscle and the cardiac muscle. So this autonomic control also controlled by the brain. In the brain, we have different centers responsible for a lot of like basic life maintenance, like heart, like thirsty, like hungry, like heart rate, like breathing. So a lot of this integration, signal integration are in the brain. The autonomic nervous system has two branches, sympathetic and parasympathetic. The way to distinguish these two is something like this figure here. Sympathetic is for fight or flight. So when you're ready to do that, your body change your mode to be more sympathetic driven situation that basically you are ready to have a fight, have a run. So your heart rate will increase, your pupil will open, you become hot, you become blood pressure increase, a lot of glucose coming in to the blood to ready to, generate force to run or to fight, to be more alert. Parasympathetic is on the other side that we start to rest. And during this time, we will reduce the heart rate. We don't need to be so alert. We could be more, relaxing. And that's a parasympathetic. So we have these two branches. So this one is showing you that all this coming from the central nervous system. Here is the sympathetic nerve coming from the spinal cord. So here is spinal cord, sympathetic, send out signal to the eye, dilate our pupil, you're ready to find, you need to see more clear. Let me see. Yeah, sorry. I couldn't see the words very clear. So small. All right. So so that's sympathetic. And for the parasympathetic, they come from the parasympathetic, the major branch, like this one here. The major branch is the vagus nerve. Vagus nerve. Vagus nerve is the parasympathetic. And also pupil and also saliva. That's because that when we are digesting, ready to digest and the rest, our saliva release them. And also our GI system, gastrointestinal too, they will release those enzymes to digest food. So one thing you need to know here is that they, so here, let me repeat again. So they come from the spinal cord or they come from the central nervous system. They come from, their connection is two nerve connection. So they don't directly, control one of these organ directly. They don't, they have like two nerve system. So here is the two nerve system for sympathetic and the parasympathetic. So here, from the central nervous system, they don't directly target the tissue, but go through another neuron. This second neuron is called the autonomic ganglion or ganglion neuron. And this one is, sometimes we call it preganglionic neuron. Sometimes we call this one postganglionic neuron, but either way that this one is preganglion or central nervous system, this one is ganglionic neuron. And do we have words like that here? All right. Okay. All right. So they are go through two nervous system. Now let's look at the sympathetic. Sympathetic central nervous system send out signal to the postganglionic or ganglionic neuron, and then this ganglionic neuron releases neurotransmitter to the target organ. Same thing as the parasympathetic central nervous system send out axon to the ganglionic neuron or post. This one can be called the pre-ganglionic neuron. This one can be called a post ganglionic neuron. Okay, so the pre-ganglionic neuron also will contact with this post-ganglionic neuron. Then post-ganglionic neuron will contact the target organ. One thing you need to memorize is the neurotransmitter. The sympathetic, when they act on the target organ, they release norepinephrine. Norepinephrine is also called androgen. Not androgen. I think it's called androgen, yes. So that's why it's called, I have to check that. All right, never mind. Norepinephrine. Norepinephrine is a neurotransmitter acts on the target organ. Let me just pause it right now. I want to make sure. Yeah. Hi, I am back. Yeah. Adrenaline, that's the term I was looking for. Adrenaline. Okay. So the epinephrine is also called adrenaline. That's why the target. Let me share this screen here. See, that's why we need the multiple choice questions. You have something to choose it from. Otherwise, sometimes you just blank. You don't rememberize it. Adrenaline. Yes, adrenaline. All right. So, this the receptor is adrenergic receptor. So what you need to memorize, I know sometimes you blank, but it will be in the quiz question because this is very common. Like norepinephrine is a neurotransmitter for the sympathetic nerve. And what's the neurotransmitter for the parasympathetic nerve? Is the acetylcholine. Acetylcholine is the neurotransmitter for the parasympathetic nerve. Okay, when it acts on the target organ. During that pre and the post, they use this acetylcholine as the neurotransmitter. So this is why it's common. But when they act on the target organ, it's either norepinephrine or acetylcholine. Adrenaline. Yes, that's the term I was looking for. In the sympathetic nerve system, they also activate adrenal cortex. Adrenal cortex is a endocrine system. It's a gland located on top of the kidney. So here is the adrenal cortex right here. Adrenal medulla. Adrenal cortex is different. Adrenal cortex is produce the steroid hormone. But adrenal medulla, this one will release the epinephrine, or called adrenaline. That can also go into the blood here, epinephrine, and go into the blood, and that will be part of the sympathetic reaction. So the quiz question will be, which endocrine system participate sympathetic reaction? That will be, the answer will be adrenal. It could be the adrenal gland. Adrenal gland is this large thing, but to be more specific, it should be adrenal medulla, because adrenal cortex produce totally different group of hormone. Adrenal medulla produce epinephrine that is function like norepinephrine and part of this sympathetic nerve system. So that's the sympathetic. The next one is the parasympathetic. So parasympathetic coming from either brain or very little here, spinal cord, the pelvic splanchnic nerve right here. In the brain, this cranial nerve participate. The parasympathetic are cranial nerve 3, 7, 9, and 10. These only 4 numbers you need to memorize, so just memorize those 3, 7, 9, and 10. 3 is the oculomotor, 7 is the facial nerve. This one parasympathetic is for digesting and resting. So this one is about saliva, growth of pharyngeal nerve. Cranial nerve 9 is also part of the salivary secretion. and the 10 vagus nerve. So this one is the vagus nerve. This one is the major one, vagus nerve. I want to talk a little bit more about this cranial nerve 3 because in the lab, even though I don't think you need to turn it in, but I think this is a good time to describe it. So when you do a lab, you know what it's about. So cranial nerve 3 is an oculomotor. So parasympathetic is part of the motor. It's controlling the smooth muscle and also heart. So this cranial nerve 3 is an oculomotor. It means that it controls our ocular, means control our eye. It controls what eye? It controls the pupil. It causes the pupil constriction, okay? So basically this is the part of the parasympathetic, and also the triggering of that response is the light. When we shine a light into one eye, it will cause pupil constriction. And it has two portions. One is the sensory, the other one is motor. So you have the light coming in. So this is sensory. This sensory goes through the cranial nerve. 2 is also called optic nerve. And then it will respond to motor, which is a pupil constriction. And this one coming through the cranial nerve 3 is called the oculomotor nerve, oculomotor nerve. So we have the light coming in and respond with the cranial nerve 3. Light coming in through the sensory. So this one is the sensory response, sensory signal, and this one is the motor. So this one goes back to very much like this very basic model, like this one here. So again, this one is sensory and motor, sensory motor. This one is right here, sensory motor. So basically very much the same. In the brain, integrated signal, sensory, optic nerve, cranial nerve 2, motor, pupil constriction, cranial nerve 3. Right here. So that's here. Sensory, cranial nerve 2, optic nerve, right here, cranial nerve, optic nerve, right here, okay? And the response is cranial nerve 3. One thing you need to know is that this pupil constriction is on both eyes. So when the sensory coming in, it will trigger the motor of both eyes. So when this one cranial nerve, it will cranial nerve 3 on left eye and the right eye. So here we have a pupil constriction of another eye. This is say left, this is right. Okay, so for example, if you shine light into one eye, and you would expect to see that both eyes have constriction, not just one eye. Okay. In our lab, we will have a question like, if you shine light on, say you have the right, say this is the left eye, say this is the left eye, this is right eye. If you shine light on one eye, but you only see constriction in this eye. Constriction on this eye. So what's the cause? where is the damage? Shylights or optic nerve? Because it constrict, it means that we must detect it. So optic nerve here is okay. And here is the cranial nerve, CN3 is okay. But what's not okay is this CN3. So this cranial nerve, CN3, this one is not okay. That's why we don't have the constriction on this side. And so the answer will be, if this one shine on right eye, we will say that right eye CN3 is damaged, but not the left cranial nerve 3. So this one summarizes all our nervous system, all our motor nervous system include the somatic motor, the skeletal muscle motor system, as well as the autonomic motor system. So we have the somatic nervous system that control our muscle constriction. The neurotransmitter is acetylcholine. The receptor is nicotinic acetylcholine receptor. This one always excitatory. For the sympathetic release norepinephrine. The parasympathetic release acetylcholine to act on the target organ. This one could be excitatory or could be inhibitory, depends on the receptor. In this autonomic nerve system, we have preganglionic. That is what I'm looking for. Preganglionic, and the postganglionic. Here is postganglionic neuron. So in the preganglionic to postganglionic, they are communicated through the acetylcholine. But when they act on the target organ, parasympathetic release acetylcholine, sympathetic release norepinephrine. So that's the quiz question, okay? Those are the quiz questions. Now in the end, we have some reference. You can just take a look. Different sympathetic and parasympathetic, how is their function. You probably see it better when you opens up this on your PowerPoint, on your PDF. It will be clear. This one just showing you their effects. You don't need to memorize. You don't need to memorize it. This is just some reference to you. So we are not going to quiz you on that. But what you need to memorize is the neurotransmitter. The neurotransmitter for the neuromuscular junction is ACH, acetylcholine. Sympathetic is norepinephrine. Parasympathetic is acetylcholine. All right. So that's it. And thank you for your time. Stay safe and stay strong, okay? And get some more sleep. Sleep is important.